Hello, my name is Louis Petit, and I will present my paper about TAPE, which is a Tether-Aware path planning algorithm for exploration of unknown cavities with a tethered aerial robot. This work was supported by the University of Sherbrooke and supervised by Professor Alexis Lussier Desbiens. Our goal is to provide an algorithm that is capable of exploring unknown cavities while avoiding tether entanglements. It was motivated by the project of a mine mapping UAV designed for the mapping of mining stopes, which are large underground cavities that can reach up to 300 meters in height. Those large environments can pose challenges for computation, autonomy, and communication. These can be solved with the help of a tether. The drone can then be powered by an external source and share data and computation with a remote computer. The tether should be retractile and kept in taut condition. To allow the robot to continue its path if the tether gets tangled somewhere, it should be stored in an onboard spool. But it will directly contribute to the payload of the robot. So our goal is to provide an algorithm that will first minimize the path cost, which is related to the mission time, and secondly, to respect the maximum tether length that will contribute to the payload. Most exploration models that exist do not consider the case of a tethered robot. Those that do are not optimized for path length, and they only consider the two-dimensional case. TAPE is constructed with a hierarchical framework since the state-of-the-art has shown that it is very effective for exploration, and it allows easier real-time computing. We also observed that the tether entanglements are strongly influenced by the local behavior of the robot, and they are almost independent of the global path. We'll come back to it later in the results section. Our two-level architecture employs a global planner that will solve a traveling salesman problem. It is responsible for path cost minimization and for respecting the boundary conditions. The local planner will evaluate several local path options. It will try to minimize the path cost as well and consider the tether configuration. The global planner first extracts the frontiers from the latest map. Then it solves a TSP for the corresponding viewpoints. Then the local planner will produce the path to the next viewpoint, and this operation is repeated with the latest sensor readings. The local planner will search for path portions, assemble and shortcut them, and determine which of them is the best solution. Path portions are generated between the robot, the contact point, the home point, and the goal. They are assembled as pictured here. And we apply two types of shortcut to some of them. Either RRT rope that will produce a near optimal path, or a tether-like shortcut that will keep the path stuck in local minima. Now we have an informed range of paths between the shortest and the total untangling path. To determine the best one, we use a decision function that takes into account the path cost, the maximum tether length, and the final tether length and contact points at goal. We tested our algorithm in 4 different simulated environments, including 2 classic mining stopes, a larger stope, and a cluttered warehouse to challenge our algorithm with a high risk of tether entanglements. The results provide 3 main conclusions. First, the global planner that solves the TSP produces the shortest path in most cases. The same global planner, but that also takes into account the tether, will produce a longer path, but it will not influence the tether entanglements as I said before. Finally, our local planner leads to a slight distance increase, but the maximal tether condition is always respected. On average, the distance increase is 4%, but the classic approach has a 47% probability of violating the tether condition. The path in green confirms that the slight distance increase allows to avoid entanglements with the rocky outgrowth on the left part or with the shelves on the right. A parametric analysis is provided in our paper if you are interested in finding the best coefficient values for the decision function. We also tested tape in a real-world flight, and the drone has successfully avoided entanglements with the pillars that you can see on the left here.
If you are interested in using our method in a maze environment, another planner than RRT rope is encouraged for path generation, but you should be warned about real-time computation. Also, our local planner can be fully integrated with any other global planner of your choice. Here is a demo of our exploration algorithm with the live path decision that you can see in the upper right corner. Thank you for listening.